Okay, good morning, everyone. So this week will be week 14, and we were trying to complete our chapters we have two more chapters, group 17 and group 18. And as you know, that there was also 1 week that we did not have class. So we will have a replacement class. Most probably I will do it asynchronously. So most probably the replacement class will be at night as well. We'll try to do that and to complete the group 17 and group 18 this week. And so that I can give you the tutorials this week and you can submit it by next week. Okay. Okay, let's carry on with our lesson today. So for group 17, it is the halogens. All right. As you can see here, these are some of the colors, the colors of our halogen. You have the chlorine, bromine, the iodine. And if you look at the physical states, all right, chlorine is in gas, all right, at room temperature. It is in gas phase. Bromine is in liquid phase, okay, and it shows a brown color, okay, a liquid. And the iodine is in solid, all right, and it's violet, purple color. And the iodine actually also can vaporize, okay, the solid forms in room temperature and pressure. It can actually also vaporize, and you can see purple fumes, okay. And halogen is also used in light bulbs, okay, halogen light bulbs to fill up the space in the light bulb, incandescent light bulb. It also helps to prevent the degradation of the filament, right? Tungsten filament normally. And this tungsten will actually ionize, all right? And it will deposit, vaporize and deposit on the inner layer of the incandescent bulb. So what happens is that these halogens can actually bind with this vaporized tungsten. And when it cools down, it can actually, this tungsten can actually redeposit back into its filament, okay, rather than having a coating on the inner layer of the incandescent light bulb. That's why you see sometimes your light bulb will turn blackling of the light bulb. It's because of the tungsten filament that has been vaporized and deposit on the inner layer. All right. Okay. So as we see here, we have from the top, you have the fluorine, okay, the chlorine, bromine, and iodine, and the astatine, all right. And most of the time, we do not discuss much on the astatine because it's a radioactive element, all right, and the half-life is less than a minute, okay. So the halogens actually from the Greek word hales, okay, it means salt, okay, and gen, which means to generate, to form salts. Okay, as you see, the halogen actually forms salts with the group 1 and group 2, and most of the ore, metal ore, as you can see, they consist of halogens. Okay, in their chemical formula. Okay. Okay, the electronic configuration, as you can see, there are 17 electrons at the valence shell. Okay, and chlorine has a valence shell in the group 3 at shell 3. So as you can see here, it also involves the d orbitals. Okay, starting from chlorine. All right, natural occurrence found as salts of the halide ion. Because of their high reactivity, they are very reactive, and so they form a lot of these metal ores. Okay, here you have the fluorine, fluorspar, cryolite. Okay, chlorine, salt, sodium chloride. It's abundant. Okay, very common. Okay, bromine, low concentration of bromine. Bromine is normally from the ocean, and iodine as well. Okay, so even the salt, the table salt that we eat, if it's highly purified, okay, it will only contain sodium chloride. If it is sometimes you can see that these salts that you buy, if they are not highly refined, they also contain iodine and bromine. Okay. All right, here are some of the physical chemical properties. Okay, physical and chemical properties. As you can see, just highlight a few. The electronegativity. Okay, fluorine has a very high electronegativity compared to the others, right? And so it's it has a slightly different chemical properties. Okay, as we will see in the following slides. As well as here the oxidation states. Okay, fluorine has a -1 oxidation state, oxidation number, and chlorine, bromine, iodine, and the others. It can form in a range of -1 to +7. Okay, right. So the halogen, we know that it can bind with 1 electron to form the an octet valence electron. Okay. Look at the density, all right, and that's why you look at the physical states. It is in gas, right, as well as the chlorine and fluorine and chlorine, and the bromine is in the liquid phase, and the iodine is in solid phase. Okay. Okay. If you look at the physical appearance, it is a colorless gas. Fluorine is a colorless gas. Chlorine, on the other hand, is a yellowish green gas. Okay. Bromine is reddish brown. It's a little bit difficult to distinguish whether reddish or brown, but it's a mixture. Mostly, I would say it's more of a brown liquid. Okay. Iodine is a violet solid. Okay, purple color. And that is why it's very easy for us to identify when we have a compound, and when we react with certain compound to form the chlorine gas or bromine gas or iodine gas, we can actually identify them just by looking at the colors. Okay. Right. So each atom has, as I mentioned, has 7 valence electrons, and therefore need only 1 electron to achieve a noble gas configuration. Okay, an octet configuration. As a result, in the elemental state, they form singly bonded diatomic molecules. So they can share with another halide, okay, to form a single bonded diatomic molecules. They can also form among the halides. So chlorine and bromine, chlorine and iodine, it can also form such a compound. Okay. And so most of the time they form diatomic molecules, okay, in the normal temperature and the at room pressure. Okay, as we look down, proceed down the group, regular increase in melting point and boiling points. Okay, so as the size, they are non-polar. Okay, the diatomic molecules are non-polar. As you go down, moving from the top to the bottom of the group, the size of the halogen increases, and so the intermolecular weak forces, okay, van der Waals forces, they increase, okay, due to the increase in the molecular weight. Okay, color intensity, okay, increases, is more and more intense as you go down the group. The atomic radius, ionic radius also increases, okay, as the shell increases. Density of the element as well. Okay, that's why we have solid for iodine, right? Regular decrease in ionization energy. So the ionization energy also decreases, okay, from top to bottom as the shells increases. The electronegativity as well decreases, okay, as the size increase. The oxidation power as well decrease. Since from the top you have fluorine, which is very electronegative, it is able to attract electrons towards itself. as compared to as we go down to the group, the iodine has much lower electronegativity. So the ability to attract the electrons towards the iodine itself, it's much weaker, and so the oxidizing power also decreases. Okay. All right, so let's look at how it is prepared industrially. So fluorine can be obtained by the electrolysis of hydrofluoride dissolved in molten potassium fluoride. Okay, so the potassium fluoride mixture serves as an electrolyte because pure HF is not conducting. Okay, it's not electrolyte. So it requires potassium fluoride. Okay, and so at the anode, it is the oxidation. The fluorine ion will be oxidized to form the fluorine gas. Okay, at the cathode, reduction is a reduction process, so hydrogen will be reduced to form the hydrogen gas. Okay, chlorine. This I believe we have discussed about this in group 1 of the elements. So here, just to recap, in the electrolysis of molten sodium chloride in down cell, so it uses a molten sodium chloride, okay, rather than a concentrated or aqueous sodium chloride. And this is the chamber, the anode, where the oxidation happens. The chlorine ion will be here will be oxidized, okay, to form the chlorine gas. Okay, and here, if you look here, the chambers are separated, okay, so that they do not react. Okay, it has to be separated, and here your cathode, all right, will be reduced. Your sodium ion will be reduced to the sodium liquid. Okay, there are also other methods that can be used to obtain our chlorine gas. Okay, which is the electrolysis of brine in Kellner-Solvay method, or using the cold alkali cell. Okay, so this the difference is that if you look between this and this method, is that in Kellner-Solvay method, it uses either Kellner-Solvay or the alkali cell. They are very similar. Okay, that they uses brine. Okay, concentrated sodium chloride. Okay, in aqueous. So and in between these two cells, Kellner-Solvay and the alkali cell, the difference is that the electrodes that they use. Okay, here the Kellner-Solvay, okay, uses mercury as their cathode. Okay, as a cathode, while the chlor-alkali cell uses other metals, okay, nickel, titanium, graphite, right, as the cathode. Okay, so as you can see here, concentrated sodium alkali is introduced into the chamber where the oxidation takes place. Okay, and at the surface of the cathode, okay, where the solution is, it takes the reduction takes place. Okay, and it flows, and so the sodium ion will flow into this chamber, all right, which is where the cathode is, and it will form an amalgam with the mercury. Okay, and this amalgam will then flow into a chamber where it will react with water to form the sodium hydroxide and hydrogen gas. Okay, and at the anode, the chlorine ions will be reduced to form, will be oxidized, sorry, to form the chlorine gas. Okay, and one important thing to take note is that the here, as you can see, there is a membrane actually. There is a membrane, and the membrane actually separates between the ions. Okay, and it allows the ions, the sodium ion, to flow into the cathode. All right, but the chlorine gas, it is not able to. So in this way, the sodium hydroxide do not react with the chlorine gas, okay, to prevent the reaction between these two compounds, because it can actually react to form the sodium hypochlorite, okay, which is very, very poisonous, and it is very caustic. So this is one of the way to prevent it, which is using a permeable membrane, okay. And this is also a very much researched area, the membrane, right? Not only in these processes, also it can be used in purification of water, for example, right? You can actually purify salt water to get drinkable water. It has been used, these membranes, in the fuel cells, okay, where it uses methanol, for instance, as a fuel, and it can actually separate certain ions that is needed for combustion. So it is very useful, and it's a very intensively researched area on the membrane. Okay. Right. The difference between the downcell and the Kellner-Solvay method, as you can see, the electrolyte used for the downcell is a molten sodium chloride. Okay. And as well, however, for the Kellner-Solvay method, it uses brine and concentrated sodium chloride. The side product for the downcell is only sodium metal. Okay. So it is relatively straightforward. Okay, as compared to Kellner-Solvay method, it produces hydrogen gas and sodium hydroxide, which is not needed actually, and it can cause complication when it reacts with the chlorine gas. Okay, however, downcell, the reaction condition is extreme. It's extreme at high temperatures, while Kellner-Solvay method can only it only requires normal temperature to react. Okay. Okay. So that is chlorine. So how do we extract bromine? So we know bromine, it is found in the ocean. Okay. So it can be extracted through oxidation. Okay. So it can be extracted by passing chlorine gas into concentrated seawater. So the bromine ion is oxidized to molecular bromine. So since we know that the halogen itself is it is an oxidizing agent, and chlorine has a stronger oxidizing power compared to bromine, so it can be used to extract bromine from the ocean, okay, from concentrated solution of ocean. So you see that these bromine gases are actually extracted in places where the salt content is very, very high, right? Where you have lakes or water that are stagnant for a long period of time. For instance, in the Dead Sea, and in certain areas where they have lakes that have no running outlets. Okay, so it vaporizes and the salt content increases in the lake. So in those areas, it will be very easy, very much easier to use this method to actually extract bromine gas. Okay. Then air is passed through the seawater to vaporize the bromine. Okay, so the bromine is actually volatile, so it actually comes out together with this with the air that it has been passed through the seawater, and the gas, the vaporized bromine, is transferred to sulfide, okay, and form a solution. Okay, and so the sulfide will reduce bromine to the bromide ion. Okay, and so it is in the solution form rather than in gas form. And finally, the chlorine gas is used again to oxidize the bromine ion back into its molecular bromine before it is distilled, when at different temperatures it is able to remove to distill the bromine, the pure bromine out of the compound. Okay. Laboratory preparation. Okay, so in our labs, we can also do these reactions. Okay, like what we have done earlier for bromine, we actually we only use the chlorine gas. Okay, to extract the bromine. So that's also one of the method. Most importantly, we have to use substance that is a stronger oxidizing agent compared to the halogen that we intend to extract. Okay. So reaction of metal halide with strong oxidizing agents such as manganese dioxide in the presence of acid. Okay, so the acid itself is also an oxidizing agent. All right, so it catalyzes the reaction. So it can form the halides. Okay, and there are two reactions. Okay, where firstly it will form the hydrogen halides. Okay, in the presence of the acid and the manganese dioxide, and then the hydrogen halide will then be in the second reaction, the hydrogen halide will react with the manganese dioxide, okay, to form the halogen, okay, and the manganese halide, right? So this is the overall reaction. Okay. Right. Chlorine gas can also be made by oxidation of concentrated hydrochloric acid with manganese dioxide or potassium permanganate. Okay. These are very common reactions that can be done in our labs. So besides, a solution of chlorine in water is readily obtained by reacting bleaching powder. So earlier, these chlorine, as you can see in the third method, it forms a chlorine gas. If your intention is to form chlorine solvated in water, then you can also use a bleaching powders where it has the, in this case, the calcium chloride in combination of calcium hypochlorite. Okay, so we can actually oxidize it, okay, to form the chlorine gas, okay, in aqueous, right? So, right, so these are in aqueous and these are in gas. Right, let's look at the application of elemental halogen. Fluorine, mainly used as fluorinated agent for organic compounds. Highly fluorinated organic derivatives are now widely used in polymers, refrigerant fluids, aerosol propellants, and non-inflammable anesthetics. Okay, so we know the fluorine has been used a lot, especially in the polymer industry. The non-stick pans that you use, Teflon, right? It's actually polytetrafluoroethylene, PTFE, okay? And refrigerant fluids, all right? Aerosol propellants, all right? They are mainly used, as you can see, fluorine itself, it's in a gas, phase. So it is very suitable as well to be used in aerosols, okay, in refrigerant fluids, okay, vaporize easily. Okay. Chlorine in the manufacture of organic and inorganic chemicals in paper, pulp industry, to bleach, okay, as a bleaching agent. In water treatment, all right, in your swimming pool, it's also being used, chlorine to disinfect, okay, in cleaning and sanitization, right? In your bleach mostly has this chlorine element in the chemical formula. Okay. Bromine mainly utilized in the manufacture of organic chemicals. Typical examples, fuel additives. Okay, it's also being used in our fuel as anti-knock property. Okay, you can look up what is the anti-knock property. Flame retardant, such as brominated diphenyl ether. So it acts as a radical scavenger. Okay, because the bromine itself, when it's heated, it will form the element, bromine element, and it can actually combine with when it forms the element, it actually binds with these radicals that ignites a flame, right? So when there is a flame, radicals are being formed, okay, during the ignition, and so bromine can actually scavenge these radicals and to form elemental bromine, okay, or hydrogen bromide, okay, and this actually reduces the chances of the elements to ignite, okay. Plant protection, methyl bromide. So there's so many others, especially in chemicals, right? In chemicals as well. Chemical for in the agriculture, okay. Fire extinguishers, okay. Tear gases, inhalation anesthetics, okay. In dyes, okay, due to its color, right? Strong purple color. Look at the chemical properties. Halogen as oxidizing agent, as I mentioned, because of the high electronegativity of halogen compared to other elements. They tend to gain electrons from other substances and thereby serves as oxidizing agent. If you look here, it can displace other compounds, other elements in a compound from the values of the standard reduction potential, electron affinity, as well as the electronegativity, as we see earlier in the table. The ability of halogen as oxidizing agent decreases going down the group. So fluorine has a stronger oxidizing power. It can displace elements that are less reactive, and iodine is a much weaker oxidizing agent. Okay. It also, when it reacts with water, right, with the exception of fluorine, the halogen reacts with water in a dispropanation reaction. Okay, so dispropanation reaction, I believe I've mentioned in our previous lessons. So in this type of reaction, the reactants, example, the halogen, serve as oxidizing and reducing agent. Okay, so let's look at this general equation. This is your halogen, all right? Your halogen gas has an oxidation of 0, oxidation number of 0. When it reacts with water, it actually forms compounds with the halogen that has the oxidation number +1 and -1. So it is in between the oxidation will increase and as well as decrease from the original halogen. Okay, so this is called the dispropanation reaction. However, based on the standard reduction potential, only fluorine and chlorine can oxidize water. So this is based on the standard reduction potential, all right? But the other elements can also react actually, but it may not be so reactive. Okay. So the fluorine also react with water, but it is not forming dispropanation reaction. Okay, it forms the hydrogen fluoride and oxygen gas. And about 30% of the dissolved chlorine exists in the form of the hypochlorous acid, okay, HOCl, and the chlorine ion. But in the presence of light, the hypochlorous acid can actually decompose, all right, to form the chlorine ion. Okay, so initially it actually exists as the hypochlorous acid when we react the chlorine and with water. Okay, but it will eventually decompose to form the chlorine ion that we know. So the overall reaction, it actually forms the chlorine ion, but the intermediate reaction actually forms the hypochlorous acid. Okay. Reaction is with the alkaline solution. It also has the dispropanation reaction. Okay, so if you see here, if you an example of a chlorine gas, okay, it will form react with the base hydroxide ion. It will form the chlorine ion and the hypochlorite. Okay, So the only difference is that when it reacts with the alkaline solution, the hypochlorous acid, as we see earlier, with the reaction with the water, the hypochlorous acid is deprotonated. So the hydrogen is deprotonated. Okay, and here it forms the hypochlorite ion, anion. Okay, and here actually we can actually precipitate it with the cation and to form, for instance, as we see earlier, the sodium hypochlorite ion. Okay, we can actually form this and precipitate this out. Okay, the hypochlorite anion also tends to disproportionate further. Okay, to form the ion and the anions. Okay. All right. Reaction with non-metallic elements. Halogens form covalent bonds. Okay, in compounds with non-metallic elements. So from group 3, 4, 5, 6, and 7. Okay, these are the compounds, and I think most of it we have discussed earlier. And as you can see, fluorine is so much reactive. Okay, and chlorine as well, right? But bromine and iodine, it's much less reactive. Okay. We will also look at the halide compounds with elements of group 17. They'll be discussed under the interhalogen compounds, where it actually binds with other halogen, okay, to form a compound, right? So some of the reaction with metals, okay, here is with metals. They are very reactive for fluorine, okay, and it reacts with most of the metals. But the chlorine and bromine and iodine, they're not that reactive in comparison with fluorine. And it requires heat, right, to form these metal complexes. Okay, some notes where the halides of the S block metals are ionic. Okay, for instance, the sodium chloride, and when it dissolves in solution, the aqueous solution, it is neutral. Okay, and group 2 halides, for instance, the beryllium and magnesium have some covalent character. As we know that the valence electrons are only 2, and it can actually, and in the, for instance, the beryllium is the valence electron is in shell number 2, and it can actually extend. Okay, when it's excited, it only occupies 2 of the orbitals of the S shell, and they are empty orbitals that can actually receive the electron pair from the halogen, okay, to form a dative covalent compound, a dative covalent bond. Okay, so it has some covalent character. Halides of D block and P block metals in low oxidation state are ionic. Okay, they're ionic. With low oxidation states, the energy required to totally remove the electrons to form ionic is much easier. Okay, as compared to metals in high oxidation state. Okay, it's much difficult to totally remove the electrons. Okay, to release the electrons. Okay, so it has a covalent character due to the sharing of electrons. Right. So we also we can test to identify these halide ions. So it's very useful, and especially in identification of the compounds that we get. Okay, so there are 3 tests that we can do to identify the halide ion in a solution. So we can add concentrated sulfuric acid and heat. Okay, if there is the halide ions, a chlorine anion, hydrogen chloride gas will be released. Okay, gas will be released. For bromine, the hydrogen bromide, sulfur dioxide, and bromine gas will be liberated. So we can actually identify just by looking at it. We will see that fumes, okay, brown fumes, reddish brown fumes will be liberated. And you also get a pungent smell from the sulfur dioxide. Okay, as if there is the presence of iodine, it will also form the sulfur dioxide the hydrogen sulfide, as well as the iodine. And so it will definitely give you a very pungent smell, okay? And the hydrogen sulfide will give you a rotten egg smell, okay? So you will definitely be able to identify, okay? Iodine, between iodine, bromine, and chlorine. And the iodine gas, okay, it's a purple, violet, so it's very distinctive, okay? So next, we can also add the silver nitrate, okay, followed by the ammonia aqueous solution. So when we add the silver nitrate, it will react with the halogen, okay? So silver will react with chlorine and ion to form the silver chloride. It is a white precipitate, okay? And it will dissolve in ammonia, all right? So ammonia actually solvates the silver to form a stable complex, okay? The bromine will actually form silver bromide, which is a yellowish white precipitate, okay? And it's also dissolved in the ammonia, but it requires concentrated ammonia, okay? Iodine, it also forms a yellowish precipitate, okay? But it sparingly dissolves in the concentrated ammonia. So by doing this test, we can actually identify, okay, the different ions. But each test actually has its each test for test A, test B, and test C. There are pros and cons, and so it might require 2 or 3 of these analysis tests to identify certain an ion. Okay, I think I have a picture over here. So these are the chlorine, the silver chloride, precipitate, silver bromide, and silver iodide. So you can see the color is for the bromide is slightly yellowish, and the iodine as well, but it's not much difference. Okay, but the intensity actually increases for the silver iodide as compared to the silver bromide, but it's very difficult to identify, okay, just by looking at it, right? Okay, another method, method C, we can add chlorine, aqueous chlorine, or acidic sodium hypochlorite, okay, and then we add in the CCl4, okay, the tetrachloromethane, right? Tetrachloromethane is an non-polar solvent. So when it reacts, okay, when it reacts with the sodium hypochlorite or the chlorine aqueous solution, it will form the gases, okay, this chlorine, bromine, iodine gas. And these gases are also non-polar, so it will dissolve in CCl4, okay. But for chlorine, it does not react, chlorine ion. Bromine gas will be released, as well as iodine gas. And when it dissolves in the organic layer, okay, it will form, there is an aqueous and organic layer, because the starting material are in the aqueous state. Okay, so you have the water solution as well as the organic layer, which is the CCl4, and they do not they're not miscible, so they do not mix the CCl4 and the water. So CCl4 is slightly dense, is denser compared to water, so it will you will see that the layer is at the bottom, and the water layer will be at the top, and you will see that the CCl4's layer it has this brown color, okay, for bromine, but for the and for the iodine it will be pink, okay, pink in color. So it's very easy to identify, right?